Hello everyone. This lecture is row reduction and echelon forms, part 2, Gaussian elimination. This content belongs to section 1.2 of our text. We're going to develop a systematic way to reduce a complicated augmented matrix to a simpler one, so-called RREF. Here, RREF stands for Reduced Row Echelon Form. And the systematic approach to obtain RREF is called Gaussian elimination. So in principle, after this lecture, you're able to solve any complicated linear system. Let's start from a simple example. 2x2 linear system. Of course, there is different way to solve out this example, but we're going to perform the row operation required by this example. So the row operation we're going to do is R1 minus R2 replace R1. So row 1 minus row 2 replace row 1. From left-hand side, comparing two equations, row 1 and row 2, we can cancel out x sub 2, and 1/2 x sub 1 is the only term remained for the left-hand side. And the right-hand side is 350 minus 300. This replaces the row 1, and row 2 stays the same. So just copy this down. So now we obtain a new linear system, but this new linear system did not change the solution set. This is key observation. So row operation does not change solution set. Based on this key observation, we can compute x1 and x2 from this reduced form. So from first new equation, we can get x1 equals 100 from here. From second equation, we can just simply write down x sub 2. This is a solution. There can be many row operations, and we're going to focus on 3 fundamental row operations which preserve the solution set. So the first one is called replacement. So it means replace one row by the sum of itself and a multiple of another row. So in the previous example, we had 1/2 x1 plus x2 equals 350 and x2 equals 300. And as an example, we had replacement. So what replacement we had is that we replaced R1 by itself plus multiple of another row, so multiple of R2. Now we can talk about the second row operation, so-called interchange. So interchange 2 rows. This is simple. So for example, we want to interchange R1 and R2. We can symbolically write down this operation as following. And then the new system we obtain from here is just switch these 2 rows and write this down. And this operation does not change the solution. Scaling. Scaling means multiply all entries in a row by a non-zero constant. So for example, I can do 2 times R1 replace R1. So which means the first row will be changed by doubling each coefficient. So x1 plus 2x2 equals 700. And the second one will be the same. Our objective in this lecture is to reduce augmented matrix into RREF. And the way to approach RREF is to perform EROs sequentially. But the question is, there are many choices of different EROs. Then which EROs should I perform? For this purpose, we provide Gaussian elimination. It's a strategy to reach the desired REF form. Now, we can divide the whole Gaussian elimination into 2 steps, forward and backward elimination. Forward elimination means make zeros below pivot from left to the right. And backward elimination means make zeros above the pivot from right to left. The key step here is how to identify this pivot. So to do that, you can follow 1, 2, 3, 4, 5. So fix leftmost non-zero column. Then you're going to choose the pivot position from this non-zero column. And if this pivot position is not the first row, then you should put it into the first row by interchange. And then make zeros below pivot if there's non-zero terms below the pivot, which means you need to have replacement. And then we are going to cover the pivot column and pivot row. So you get smaller matrix, and then going back to step 1. So you could take the leftmost non-zero column again from the smaller matrix, repeating until the end. And backward elimination is straightforward. It's just doing replacement to eliminate non-zero terms above the pivot. So this is replacement. Now we're going to try one example given by 3 by 3 linear system, and there are 4 quadrants. Find RREF. Is it consistent? If this is consistent, does the uniqueness hold? Final quadrant is solve it. So we first start with augmented matrix, which can be written as 1, 2, -1, 4. Just pull out all the coefficients. -1, -1, 2, 1, and 1, 0, 1, 6. I need more space for the computation. So I'm going to copy and paste it to the next page. From the Gaussian elimination, first thing is to identify non-zero leftmost column, which is the pivot position. So from here, we can see that this is non-zero column from the leftmost. And we can choose one of 3 non-zero term. And I'm going to, it's up to you totally. And I'm going to choose this one as pivot position. So once you identify pivot position, we're going to get rid of everything below this pivot position. To do that, I'm going to first get rid of this negative 1, which means I need to change R2. So R2 plus, with the help of R1, which means I need add R1. So we get 1, 2, negative 1, 4. So R1 is unchanged, but R2 will be changed to 0, 1, 1, 5. Third row is unchanged. Now the next target is this one. To get rid of this, we again replace R3 by the help of R1, which means I need to subtract R1. So first two rows unchanged. Just copy this down, 0, 1, 1, 5, but the third row will be 0 and negative 2, and 1 minus negative 1 is going to be 2, and 6 minus 4 is going to be 2. Now what you do is, for the next step, I'm going to cover this pivot row and pivot column and try to work on this smaller matrix from starting over the pivot position. So the pivot position for this small one is going to be this guy. And then try to eliminate this negative 2. To do that, replace R3 by R3 plus, this time I need help from R2, so twice of R2. Then first row is unchanged, second row is going to be unchanged, the third row will be changed, now this can be the end of the forward elimination, but for simplicity we can do one further step to normalize the third row, which means I want to change 4 into 1. So what we do is scaling this time, not replacement. 1/4 of R3 replaced R3. So first rows will not be changed again. But the third row, these two spots, will be changed by dividing 4, so 1 and 3. Great. This is forward elimination. Now we do the backward. Backward means we move from right to the left. For this purpose, I'm going to mark all the pivots. And from rightmost pivot, I'm going to eliminate these two zeros above the pivot. To do that, I do EROs, replacement. First target is this guy. What you do is, I should change R2 by R2 plus, with the help of R3, so negative 1 times R3, essentially subtraction. And after this, I can target on this guy, which means I need to change R1 with the help of R3, but this time I simply add R3. So if you do this sequentially, then you can end up with following simplified form, which is, so 0, 1, 0, and 2. in the first row is 1207 if all my calculation is correct. And then the next target is this 2 because this is next pivot and above the pivot is non-zero, so I need to change 2 to 0. To do this, I'm going to change R1 replaced by R1 plus negative 2 of R2, which gives me the same thing for second row and the third row. But the last row, no, I mean the first row, we have 1, 0, 0, and 3. This is RREF. And this is the question of the first one. The next question is if the system is consistent. So to answer this question, we need RREF. And I'm going to copy this to the next page. First of all, let me recall the rule to identify a consistent system. So if a system is consistent, then the last column shouldn't be pivot column. So a consistent system is equivalent to last column is not pivot. So we can look at 3 to 3, which is last column, and it is not pivot column. So our answer is that yes, it's consistent. Now, next, the third question is about uniqueness. So for the uniqueness rule, we have the following. So if a system is consistent, then the uniqueness holds if and only if there's no free variables. So uniqueness holds if and only if there's no free variables. But what do we mean by free variables? If we recall its definition, the free variables are the variables corresponding to non-pivot columns in the coefficient matrix. In other words, this is the same thing to say there's no non-pivot column in coefficient matrix, not augmented matrix. So if we look at the coefficient matrix here, then every column is pivot column. In other words, there's no non-pivot column in coefficient matrix. So the answer is yes, it has unique solution. Then what is that unique solution? That's the last question. So to do that, we're going to convert this REF into linear system. So first equation is x1 equals 3. The second one, x2 equals 2. x3 equals 3. This directly gives the final solution. The second example is taken from the first example, the last 2 rows, and very similar, and it's a good exercise. I'm not going to get into show every detailed computation, but you can do it by yourself as exercise. And I'm going to give the final solution to verify your work. And so augmented matrix, it's straightforward. I'm not going to write it down. But after a sequence of EROs, you will end up with RREF of this kind. Um, it is 1, 0, 1, and 6. And the second row is 0, 1, -3, -7. Which means this is free variables. Number 2 is consistent. Yes, because the last column is not pivot. Number 3, uniqueness. Uniqueness does not hold because there is free variable. Here x3 is free variable. x3 is free variable. Number 4, solve it. So if there is no uniqueness, then you should find out infinitely many solutions. And it can be written in terms of free variables. So let's say first convert everything into linear system from RREF. So that means if I set the first free variable, which is x3, as let's say C1, C1 can be taken any real number, then the linear system can be written as x1 plus C3 equals 6. And the second row is x2 plus -3C1 equals -7. And that gives me the final solution, where C1 is an arbitrary number. So this is a solution.